This question is about compounds containing fluorine. Draw the shape of a molecule of krypton difluoride. So we know that krypton's in group 8, so it has 8 outer shell electrons. We've joined 2 fluorines to it, so that means that there are 10 electrons around the central atom, or 5 pairs. But we only have 2 bonds. So we need to draw a diagram. And when I would do this, I'd be in pencil thinking, if I had 5 pairs, it would look like this. 1 up, 1 down, 1 out to the side, and then the triangle. So it's like the trigonal planar centre. Okay. But if we've only got 2 Fs to attach and we want our lone pairs to be as far apart as possible, remembering that this angle around the middle is 120, this is 120, but this is 90. What we would want to do is put the lone pairs as far apart as possible. And so we're going to put them around the centre so that each lone pair, because remembering lone pairs repel more, each lone pair is 120 degrees apart, whereas if we put one at the top or the bottom, they'd only be 90 degrees from the centre. And so we end up with this shape here, and that is in a line, so we call that linear, which means that the angle is 180 degrees. Then it says there are 2 lone pairs of electrons on the oxygen atom in OF2. Explain how lone pairs on the oxygen influence the bond angle. So this is this idea that lone pairs repel more than bonding pairs. And so the angle let's just call it the bond angle. I was going to write between bonds, but it would be quicker to call it the bond angle, is going to be reduced, and it's reduced 2.5 degrees for each lone pair. So 4 pairs is usually equivalent to 109.5 degrees if they're all bonding pairs, but so 2 bond pairs and 2 lone pairs is equivalent to 109.5 minus 2 lone pairs of 2.5. So we're going to end up with a bond angle of 104.5 degrees. It's going to be reduced by the lone pairs. Silicon tetrafluoride is a tetrahedral molecule, so SiFF in a tetrahedral shape. Deduce the intermolecular forces. Well, we know that fluorine is the most electronegative element in the periodic table, so these would be delta minus, silicon would be delta plus, but the problem here is that this is a completely symmetrical molecule, and therefore the dipoles are going to cancel out, and the molecule itself has no overall dipole. As a result of having no overall dipole, this is a non-polar molecule, okay? So the only intermolecular force it has is van der Waals. So we've got, that was that bit, but now we have to explain how van der Waals arise and why there aren't any dipole-dipole forces in SiF4. So how do van der Waals arise? Van der Waals arise from movement of electrons creating a dipole, a temporary dipole in the molecule. So we get this temporary dipole in the molecule. This causes the next door neighbours. So it induces a dipole in the neighbouring molecule. They can then attract, and that's a van der Waals. Why aren't there any other forces? SiF4 is symmetrical. So what we can say is that the dipoles in SiF4 and SiF, so they cancel, and SiF4 is non-polar, and that's why there are no other forces. It obviously can't have hydrogen bonding because it has no H bonded to NO or F.